Hello everyone, welcome back to my YouTube channel. This is Sahana LK from 5th Sem Tejas section. Currently I am pursuing my engineering in SVCE Bangalore under the Department of Electronics and Communication Engineering. Today I am here to discuss about the subject of digital communication. In that I chosen a topic of the block diagram of non-coherent detection of FSK signals. Let us go through the non-coherent detection of FSK. Here, the requirement of estimating the carrier phase for the M signals makes coherent demodulation of MFSK signals very complex. As for FSK, a non-coherent demodulation is preferred which does not require the estimation of carrier phase. Tone spacing. FSK is usually implemented as orthogonal signaling where each tone means sinusoidal in the signal set cannot interfere with any of the other tones. For coherent detection, the orthogonality condition leads to a condition on tone spacing, which is given by 2 pi into f1 minus f2 into 2, which is equals to k into pi, where k is called the constant of non-coherent detection, or f1 minus f2, which is equals to k divided by 2t. Therefore, for coherently detected FSK, the spacing between frequencies is k by 2t with minimum spacing of 1 divided by 2t. For non-coherently detected FSK, the orthogonality condition leads to a condition on the frequency spacing is given by 2 into pi into f1 minus f2 into t, which is equals to 2 into k into pi. For non-coherent FSK, the frequency spacing is therefore k by t with a minimum spacing of 1 by t. For the same symbol rate, coherently detected FSK occupies less bandwidth than the non-coherently detected FSK. Let us go through a non-coherent detection of FSK quadrature receiver. In this quadrature receiver, for a non-coherent detection, phase measurement cannot be exploited. Nothing but the coherent receiver is modified as follows. For a frequency f1, the two correlations are implemented. One to correlate with an in-phase reference signal and the other to correlate with a quadrature which is 90° out of phase for the reference signal. We have the equation that phi1 which is equal to under the square root of 2 divided by t into cos of 2 pi f1 into t. As like that equation is for the in phase, this equation is for the out phase, where phi 1q is equal to under the square root of 2 by t into sine 2 pi f1 t. Here we can see the difference that in the in phase we are using the cos, in the out phase we are using the sine. For this reason, a non-coherent detector therefore requires twice as many channel branches as a coherent detector. The diagram below illustrates a non-coherent receiver for the detection of binary FSK is nothing but BFSK. Let us go through the block diagram of the non-coherent detection of the FSK. Here we can see this is the upper part and this is the lower part. In the upper part, these are the two branches are configured to detect F1 and the lower two branches are configured to detect the F2, which is this is the lower part and this is the upper part. If the received signal is of form cos 2 pi into ft plus n of t, where the phase is 0° and the frequency is f1 and the top branch of the receiver would yield the maximum output. The second branch would yield a near zero output since the reference signal of the coherent quadrature is orthogonal to the signal component. The third and fourth branches would also yield near zero output since their F2 reference means frequency which is reference signal are orthogonal to the signal component. If the received signal is of the fourth from cos 2 pi ft plus phi. The receiver signal will partially correlate with the cos of 2 pi ft into t, which is a reference signal which we have considered, and partially correlated with the sine of 2 into pi into ft, which is a reference signal. And the third and fourth reference signals are still written near zero value due to the orthogonal, which we have discussed same in this slide. The receiver is therefore able to decide whether the received signal was an F1 signal or the F2 signal. Signal by squaring and comparing them with the sum of the squares of the outputs from the lower two branches, where R1 is given by R1 square is equals to R1 square plus R1Q square, where R2 is given by R2 square is equals to R21 square plus R2 into Q square. The decision criterion is given by R1 square, which is greater than the R2 square, where R1 square minus R2 square is greater than 0, which we can choose as a S1. R2 square is greater than the R1 square is nothing but R2 square minus R1 square, which is greater than the 0. We can choose it as a S2. A receiver based on this decision criterion is known as quadrature criterion. Is nothing but quadrature receiver. Thank you.